Hello, everyone. Thank you so much for listening in. Today, I thought I will talk about unsupervised learning. This will be part one of a lecture series on unsupervised learning and visualization with a focus on sort of concrete case studies. In the first part, I will just give a very brief overview of unsupervised learning. And in the second part, I will talk about visualization and unsupervised learning and motivate it with some practical examples and case studies from projects that I was involved in. I will just quickly share my screen. So in order to sort of understand this division between unsupervised and supervised learning, one needs to understand what is supervised and what is unsupervised. And very briefly, supervised means that humans have assigned labels to certain data points. That is, they have categorized it into different categories. And these categories are made by humans. And this is what we call a label. So, for example, here is some data. This is all taken from Google's course on unsupervised learning. There's some data on restaurant tips. On the x-axis is total bill amount, and on the y-axis is the amount of tips. And as you can see, as the bill increases, the total amount of tips also increase. You can also see that this plot is sort of categorized into two categories. One is pickup and another is delivery. That is, this restaurant is doing these two different modes, that is pickup and delivery. And in this case, pickup is a label. That is, humans have sort of categorized this data as that particular data point is a pickup, denoted by blue points, and the points in yellow are deliveries. So this is what's implied, that the data is already labeled. We are learning from these past examples and we are trying to categorize it. So a problem in machine learning may be that given the amount of tips and the total bill amount, can you predict, given past examples, can you predict whether this is a pickup or a delivery? And a machine learning model would be trained on past data. That is, there would be tip amounts, there will be bill amounts, and there would be a label, pickup or delivery. There's the past data. And then given some held out data, you have to predict, given the bill amount and the tips, whether that particular order was a pickup or a delivery. So that is called supervised learning. In this case, there is this, you have some input data in supervised learning denoted by X here, and there is some model. There can be many, many different kinds of model. It can be a linear regression. It can be a logistic regression. It can be a neural network. And that is all denoted by this function f. And you have a certain model output y, which are these labels. That is, this is supervised. In unsupervised learning, the data is not labeled. And this is a big challenge because this really means that those labels do not exist. So the challenge is to find out patterns in this data and figure out if the data naturally falls into different groups or not. So for example, again, from this Google course, there is some data here. On the y-axis is income, and on the x-axis is years that employees have spent at a company. And again, you can see that there is a linear increasing trend. As employees spend more years at a company, they have more income. But interestingly, this data seems to fall into two groups. That is, there is a section of employees who are fast track. That is, they are achievers, they're super achievers, they are on sort of a fast track. They're doing much better than peers in the other group, given the amount of years that they have spent at a company. Their income is much, much higher, and they are on fast track. So the human eyeball, we can sort of eyeball this and find out that there are patterns. But the challenge here is to use a computer program, some machine learning approach to do that. And there are many, many unsupervised learning approaches. There is clustering, there is principal components analysis, there are autoencoders, there are sort of these tree-based clustering approaches, k-means, k-nearest neighbors. There are many, many unsupervised learning approaches. But the basic idea is that there is no label. That is, nobody has told us whether there is a fast track employee or not, or whether there is such a category. The idea is to look at novel data that you have just received and find patterns, with the idea that this is just a tool for hypothesis generation. One never sort of does an unsupervised learning approach and finds out new patterns and then sort of makes a decision based on that. There is always a reflection. Why did we find these patterns? What do these patterns mean? You talk with the people who generated the data, you talk with the domain experts, and you figure out what is really happening. So unsupervised learning is really a bridge to understanding your data rather than the be all and end all. In this case, I will talk about one particular approach called principal components analysis. So this looks at the amount of variation in the data and tries to find a lower dimensional representation. Now that may sound very fancy, but let me demystify that for you. So in this case, here is some data that's on this two-dimensional plot. These are all sort of scattered, but you will see that there are very few data points on the upper left quadrant and the lower right quadrant. So the data sort of instinctively falls into this pattern here where it seems to lie along this line, suggesting that the data is really not distributed uniformly in these two dimensions, but seems to cluster along the single line that stretches from the lower left-hand side to the upper right-hand side of this diagram. I'm not sure if you can see my mouse cursor here, but this is the line along which this lies. And we can formalize this notion. We can say that, can we find a line that captures most of the variation in the data? And that is shown in this animation here. As we rotate a particular line, there is only one particular line that captures most of the variation in that. So for example, as this line rotates, this perpendicular line does not capture most of the variation, since the distance from all these points to that line is quite high. But this line right here captures the maximum variation, because the distance between that line and all the different points on it is actually minimized. So it captures all the variation that the data has in a single line. Now, that is dimensionality reduction, because we have gone from 2 dimensions now into 1 dimension. So that is the basic intuition that principal components analysis, or PCA, tries to capture. So for example, again, on the left-hand side, this is taken from the book, The Introduction to Statistical Learning in R by Tipshirani et al. You see some data that's distributed in 3 dimensions. But again, if you just eyeball this, you can see that most of the data seems to lie on this plane. Like there are no data points right here in the lower left quadrant or no data points in the upper right quadrant. Most of the data points seem to sort of cluster around this single plane. So this is three-dimensional data, but the intuition is that there is a two-dimensional plane. That is, we can go from 3 dimensions to 2 dimensions without losing a lot of information. And that is really key. We want to capture the most information as we can while still going into a lower dimension. So we can go from 3 dimensions right here to 2 dimensions on this right-hand side diagram. You can see that this is a 2-dimensional representation of the data that captures most of the variation that the data has. So this is now, even though we have lost a little bit of information, but still we have captured sort of the essence of the data, and we have reduced 1 dimension. That is, we have gone from 3 dimensions to 2 dimensions. And the idea is that again, the variance or the amount of variation in this data in this particular plane is actually maximized. And way PCA does that without getting into a lot of mathematical details is by taking a linear sum of all the different input features. So for example, if you have data that has input features x1, x2 up to xp, you take a linear combination of all those features and then compose a new feature, z1 in this case. And the key idea is that it is linear. So there is no term here that is like x1 times x2 or x1 squared or x2 squared. This is linear in terms of the input features. If you accept this restriction or this assumption, then you can find a new sort of lower dimensional sort of plane, if you will, or feature, a new feature, Z1, which is now a linear combination of the original input features. So this is an assumption that PCA makes. I will come back to the slide in a few minutes. But the key idea in dimensionality reduction is that you have these, what's called an information bottleneck. That is, you have these input features, you compress it or encode it, you go into a lower dimensional representation, that is this code, that captures most of the information that the original data has, such that if you wanted to reconstruct the original data, that is, go in this direction, if you want to decode it, you can reconstruct this original data. And there wouldn't be much difference between these two, between the original data X and the reconstructed data X hat. So that's this concept of information bottleneck. And it's a very, very important concept. I will keep coming back to that again and again. But that is the underlying concept behind most, if not all, dimensionality reduction techniques. Now, there are many applications of this idea. You can use it to find structure in movie ratings. That is what Netflix and other sort of movie recommendation websites do. They have huge databases of different patterns in sort of movie ratings. And as it turns out that you could look at millions and millions of users and what kind of movie ratings they have given. And there is like a lower dimension representation of that data. That is, most of these users, you may think that, oh my God, there are millions of users. How can I find any patterns? But most users fall into a few categories, like I'm a science fiction fan, or somebody likes romantic movies, or somebody likes some kind of action movies, or somebody likes dystopian science fiction and things like that. So that is what I mean by you can go from 1 million users to maybe 4 or 5 different categories. And that is what I mean by dimensionality reduction. You can use it to find patterns in consumer behavior. So if you are Tesco or Sainsbury or some other company, and you have data on millions of users and what they are buying, you can use that to find out, well, maybe somebody likes health foods, or somebody likes some kind of a special drink, and you can recommend those products to those users. And you can use it for example, AI in healthcare, and stratify patients and find unique features of different patients. Patients might fall into different categories, and a particular category of patient might respond well to a particular drug that he could recommend to that patient. So that is sort of the idea. There are lots of assumptions again that, for example, PCA makes. Again, going back to this particular equation, this is a linear sum of all the input features. So, for example, one assumption that PCA makes is linearity. That is, there is a linear relationship between the data points and the lower dimensional representation. One can relax this, and we can see what that means when that happens. There is also this concept of a loss function. And if you go back to this particular animation here, I said that we want to have this line right there that captures most of the variation. And as you can see that you find these red lines between each of the data points and the particular line. So the blue points are the data points, and the red lines are the distance between those data points and the line. And we want to minimize that particular distance. We want to minimize that all the distances between each data point to that particular line. And that particular line right there does that. So implicitly, we are using what's called the sum of squared loss. That is, you take the distance between each point right here, this blue point right here, and the line, and that distance right there, you square it, and you sum up the distances for all of the data points. And you square it because you don't want like negative distances. We are not interested in negative distances. We just want either the absolute value or the square in this case. So implicitly, PCA assumes that there is a squared loss function that is a sum of squared loss. And then PCA uses the dot product, which is one type of inner product, which, without going into a lot of technical details, inner product is the generalization of distance or length in sort of arbitrary dimensions. So these are all the assumptions that PCA makes. You can relax these assumptions, and this would lead to algorithms like Disney, for example, which uses a different loss function in this case, or an autoencoder, which has a nonlinear loss function and a different kind of distance metric. So these are all these algorithms like Disney and autoencoder, which you might encounter in machine learning. These are all generalizations of this powerful idea that you want to compress data. There is this information bottleneck. You want to compress data and find a sort of a more parsimonious or a more sparse representation of the data. And this is a very, very important concept. There are many sort of coding exercises, and I will outline a GitHub repository that has these resources as well. But even before you code it up, I, for example, like to play around with the data without even coding it up first. And this browser-based tool right here will actually allow you to do that. So you can go to this website, you can upload your own data or use data that's already available here and try out all these different algorithms and get a feel for what these dimensionality reduction techniques are really doing. And again, this is a free sort of resource. You don't need to do any software installations. You can just go to this particular URL in your browser and play around with all these algorithms. All the material, there are code and exercises and different activities are available in this particular GitHub repository. I didn't have a chance to really go into the technical details and derivations of like PCA and all the underlying sort of mathematics behind that. If you're interested, there is a write-up, a PDF that is available in this particular link. Please do go through that and take a look. And if you have any questions, just leave a comment in the YouTube video or email me. My email addresses are available in this particular repository. Thank you so much again. And again, in part 2 of this lecture, I will talk about visualization and the pitfalls of visualization with some motivated case studies and examples. Thank you so much for listening again, and see you next time. Thank you.